Close your eyes for a moment and imagine holding a stone in your hand. It has no extraordinary appearance. It is rough at the edges, cool to the touch, and fits comfortably in your palm. If you found it on a riverbank, you might skip it across the water without a second thought. You might set it down and walk away, never thinking about it again. But if that stone were among the oldest on Earth, you would be holding something that no telescope has ever equaled in its reach backward through time. You would be touching a surface that existed before the oceans as we know them, before the mountains we have named, before almost every living thing that has ever drawn breath on this planet. In your hand, in that quiet, ordinary stone, would be locked a record of the world in its infancy, a world so alien, so ancient, and so far beyond the boundaries of the imagination that even the scientists who study it speak of it in careful, reverent language. This is a journey into the oldest rock crux on Earth, not a list of facts, not a lecture, but a slow, considered passage through deep time itself, through landscapes that no eye ever witnessed, through events that left their signatures in stone but have no other witnesses, through an Earth so different from the one you know that it might as well be a foreign planet. And yet, it is the very foundation of everything you stand on. Tonight, we are going back, further than history, further than civilization, further than any story you have ever been told. We are going back to the beginning of the solid world, and the stone in your hand is our guide. Before we can travel into the deep past, we first have to understand what rock actually is, because the word is deceptively simple. You use it every day. You have walked across it, built with it, painted with it, and shaped it into tools. But rock, in the way a geologist understands it, is something far more remarkable than its ordinary name suggests. Rock is time made solid. Every piece of stone on Earth formed at a specific moment, under specific conditions, through specific processes. And the evidence of all those conditions is still locked inside it, waiting to be read by those who know the language. Heat leaves its mark in the way crystals grew. Pressure shows in the way layers were folded or broken. Water speaks through the minerals it left behind as it passed through ancient cracks. A geologist standing in front of an exposed cliff face does not see a wall of rock. They see a timeline, a record layer by layer of every change this piece of the planet has experienced. And the older the rock, the longer the story. When scientists speak of the oldest rocks, they are using a very precise definition. They are not simply talking about rocks that formed long ago, in a geological sense, the way a mountain range might be described as ancient. They are talking about rocks formed in the first chapter of Earth's existence, a chapter so remote in time that it sits at the very edge of what human minds can meaningfully hold. The Earth is approximately 4.5 billion years old. 4.5 billion years. It is a number that passes through the mind without quite landing. So consider it this way. If you were to compress the entire history of the Earth into a single year, January 1st, the oldest rocks we have found, would appear in roughly the second week of that year. The first dinosaurs would not appear until mid-December, and all of recorded human history would fit into the last few seconds before midnight on December 31st. The oldest rocks sit so far back in that year that what came before them is largely silence. What we call the Hadean Eon, named for Hades, the ancient underworld, is the age before the solid crust fully formed, an age when the newborn Earth was a world of chaos, heat, and collision. The surface was not a surface in any familiar sense. It was a churning ocean of molten rock, a magma ocean that glowed in the dark of a young solar system still settling into its orbits. The moon itself had only recently formed, blasted loose from the young Earth by a collision so immense it reshaped both bodies forever. This is the world that the oldest surviving rocks were born into, or born just after. They are the first fragments of solid crust to harden and persist. The survivors of a world in which almost nothing survived. To hold the oldest known rock on Earth is to hold something that endured a gauntlet no younger stone has ever faced. And that story begins quietly in Canada. There is a place in Canada's Northwest Territories, deep in the wilderness near the Acasta River, where the ground opens up to reveal something extraordinary. The rocks here are gray and banded, their surfaces etched with the kind of folded patterns you might find in polished marble. They look beautiful in a modest way. If you did not know what you were looking at, you might assume they were simply decorative, interesting but not remarkable. But these are some of the oldest known rocks on Earth. The Acasta gneiss, as scientists call them, are approximately 4.03 billion years old. Let that settle in for a moment. 4 billion years. That is older than the earliest microbial life, older than the first signs of an oxygen atmosphere, older than the entire history of complex multicellular life combined, several times over. The name gneiss, pronounced nice, refers to a specific type of rock formed under extreme heat and pressure deep within the Earth's crust. It is a metamorphic rock, meaning it began as something else and was then transformed. Heat pressed into it from below. Pressure squeezed it from every direction. Over millions of years, its original minerals were rearranged into new forms. The banding you see in gneiss, those alternating light and dark stripes, is the record of that transformation. Lighter minerals like feldspar and quartz were separated from darker ones by the forces working inside the crust. When you trace one of those bands with your finger, you are tracing a line that was drawn by the very first movements of an infant planet learning how to organize itself. The Acasta gneiss was not discovered with great fanfare. It came to scientific attention gradually, as geologists working in the remote Canadian Shield began to realize that certain outcrops in the region were far older than anything previously measured in that area. Radiometric dating, the technique of measuring the decay of certain radioactive isotopes within a rock sample, gave the first hints of an extraordinary age. Multiple rounds of testing confirmed it. The rocks were genuinely ancient beyond previous expectation. The Canadian Shield itself deserves a moment of attention. It is one of the exposed cores of an ancient continental craton, a term for the oldest, most stable portions of a continent. Cratons are where the deepest roots of the continents lie. They have not been recycled back into the mantle in the way younger crust has. They have endured. They have drifted, yes, and been overridden by younger rock in places, but at their core they are the ancient bones of the Earth, still showing above the surface. Standing on the Canadian Shield is standing on one of the most stable pieces of crust on the planet. The rock beneath your feet there has not been at the bottom of an ocean for billions of years. It has not been melted and reformed. It has simply been there, carrying its age patiently, while the rest of the world churned and changed around it. The Acasta outcrop is one of the deepest exposed windows into that ancient stability, a window into a time when the rules of a young Earth were still being written. But the Acasta gneiss, extraordinary as it is, may not hold the record. In the remote subarctic terrain of northern Quebec, along the eastern shore of Hudson Bay, there is a strip of greenish rock that has quietly generated decades of debate. The Nuvvuagittuq Belt, whose name comes from the Inuktitut language and refers to a place where things are shaped in a certain way, is a narrow band of rock that some scientists believe may be the oldest known on Earth. The age estimates for these rocks range from approximately 3.8 billion years, which would already make them older than most of what we know, to as much as 4.28 billion years, which would push them back closer to the very beginning of the solid Earth than anything else yet discovered. Why the uncertainty? The problem with aging the oldest rocks is that the techniques used become increasingly difficult to apply as you push further back in time. The minerals within the rock have gone through so much transformation over billions of years that reading their isotopic ratios cleanly is enormously challenging. Different dating methods sometimes give different answers, and the debate between teams of scientists over exactly how to interpret the data can last for years, even decades. What is not in dispute is that the Nuvuagituk rocks are extraordinarily old, and what they contain is perhaps even more remarkable than their age alone. Embedded within certain layers of the belt are structures that some researchers interpret as evidence of ancient microbial activity. Tube-like filaments of a mineral called hematite, rosette-shaped formations, tiny filamentous shapes that under careful analysis seem to bear the hallmarks not of purely geological processes, but of biology. If these interpretations are correct, the Nuvuagituk belt may contain the oldest known traces of life on Earth, life so ancient that it predates even the widely accepted oldest fossils by hundreds of millions of years. This claim remains actively debated. Some scientists argue that the structures could have been formed by purely chemical and geological processes without any involvement of living things. The evidence is ambiguous, they say, and extraordinary claims require extraordinary evidence. Others look at the same formations and see something unmistakably biological in their complexity and arrangement. The argument is unlikely to be settled quickly. These rocks exist at the very edge of what our tools can resolve. In an age so remote that even the best techniques in modern geochemistry are pushed to their limits. But this uncertainty is itself a kind of wonder. To be standing at the threshold of the oldest evidence of life on Earth, peering through a fog of time so thick that even science struggles to see clearly, is to appreciate just how deep a mystery the ancient Earth truly holds. Somewhere in that greenish rock on the shores of Hudson Bay, there may be a story of the first living things, the first cells, the first organisms to capture energy from the chemistry of a young planet and use it to persist, to grow, and to leave behind a trace. And that story, if it is there, is written in the oldest stone. There is another chapter in this story of ancient Earth, and it is written not in whole rocks, but in single crystals so small that you could fit dozens of them on the head of a pin. In the Jack Hills of Western Australia, in the sun-bleached, red-dusted outback, where the land stretches toward every horizon with an almost aggressive flatness, there exists a layer of rock known as a metaconglomerate. It is an ancient sedimentary rock that was later transformed by heat and pressure, and within it, embedded like seeds in bread, are grains of a mineral called zircon. Zircon is one of the most remarkable substances in the natural world when it comes to the keeping of geological time. It is chemically stubborn, where other minerals break down, react, or recrystallize over geological ages. Zircon holds its original composition with extraordinary fidelity. It also contains uranium, which decays at a known rate into lead. By measuring the ratio of uranium to lead within a single zircon crystal, scientists can determine, with astonishing precision, exactly when that crystal formed. The Jack Hills zircons have yielded ages of 4.4 billion years. 4.4 billion years. These tiny crystals are the oldest material of terrestrial origin yet found on Earth. They predate the Acasta gneiss by nearly 400 million years. They formed when the planet was barely 100 million years old, a cosmic infant still cooling from the violence of its formation. But what makes the Jack Hills zircons even more remarkable than their age is what their chemistry says about the conditions in which they formed. The ratio of oxygen isotopes within certain crystals and the presence of particular chemical signatures suggests that liquid water existed at the surface of the Earth when these zircons crystallized. Liquid water, 4.4 billion years ago. This was profoundly unexpected. The prevailing view of the Hadean Eon, before these zircons were analyzed in detail, was that it was a hellish period of unrelenting heat, in which the surface was molten or near molten, and no water could exist in liquid form. The very name Hadean evokes this image of a world unfit for anything we associate with habitability. But the zircons tell a different story. They hint at a more nuanced early Earth, one in which the crust cooled more quickly than models had assumed. pockets of liquid water may have gathered on the surface within a few 100 million years of the planet's formation. Not a warm, gentle ocean like the ones we know today, but water nonetheless. Water under a sky thick with carbon dioxide, bombarded by meteorites from a solar system still full of debris. But water, this matters enormously, because water is the solvent of life. It is the medium in which chemistry becomes biology. And if water was present on the early Earth far sooner than we thought, then the window in which life could have originated also opens earlier than previously imagined. The Jack Hill zircons are not rocks in the conventional sense. They are fragments of early crust, compressed and carried and redeposited over billions of years until they ended up in that layer of metaconglomerate in the Australian outback. The rock that holds them is far younger than the crystals themselves, but the crystals survived intact, carrying their 4 billion-year record through every transformation around them. Holding a Jack Hill zircon, if you could see it clearly, would mean holding a grain of the original crust of this planet, a surviving piece of the Earth's first solid skin. To fully appreciate the oldest rocks, you have to first understand the world that came before them, the world in which no rock could survive, or barely could. The Hadean Cone stretches from the formation of the Earth roughly 4.5 billion years ago to around 4 billion years ago, and it is a period that has left almost no direct geological record. This is the silence before the stone. When the solar system was young, it was a disk of gas and dust circling a newly formed star. Within that disk, gravity slowly gathered particles into larger and larger bodies. Rocky planets like Earth accreted over millions of years, their surfaces growing through the constant impact of smaller objects. The heat generated by these collisions, combined with the decay of short-lived radioactive isotopes within the young planet, was immense. The Earth melted, not partially, not in places, but globally. The entire planet liquefied into a magma ocean that covered the surface from pole to pole. In this state, the denser elements sank toward the center. Iron and nickel fell inward to form the core. Lighter silicate materials rose to form what would eventually become the mantle and the crust. This process of differentiation took millions of years, and while it was happening, the surface remained a glowing, turbulent sea of molten rock. Then came the late heavy bombardment, or rather, what scientists believe may have been an intense period of meteorite and asteroid impacts, corresponding roughly with the Hadean Eon. The evidence of this period is written in the craters of the Moon, preserved there because the Moon lacks the geological processes that have erased such craters on Earth. At its height, the bombardment delivered enormous amounts of energy to the surface of the Earth, remelting the crust in affected regions, vaporizing any water that may have gathered, and resetting the geological clock in those areas. It was a world in which persistence was nearly impossible, and yet the zircons from Jack Hills survived. The first scrapped crust that formed during brief intervals of cooling managed to hold together long enough to carry their record through to us. Not the rock itself in most cases, but individual crystals within it, tiny chemically sealed capsules of the earliest Earth. There is a kind of miracle in this. In a world designed, it seemed, to erase all records, something survived. Something always survives. The scientists who study the oldest rocks are a particular kind of person. They tend to be patient. They tend to be comfortable with uncertainty. And they tend to have a relationship with time that is unlike almost any other profession. Most of us experience time on the scale of a human life. We think in decades. We occasionally stretch our imagination back to the centuries of recorded history, or perhaps to the millennia of ancient civilization. But the geologist who works with Hadean and Archean rocks must think in billions, must hold the reality of billions of years in their mind as a working dimension, the way an architect holds three-dimensional space. The tools they use are extraordinary. Mass spectrometers that can measure the isotopic composition of a sample, smaller than a grain of salt. ion microprobes that fire a beam of charged particles at a spot a few microns wide on the surface of a zircon crystal and analyze what comes off. Electron microscopes that reveal the internal structure of minerals at the scale of individual atoms. But the interpretations always require imagination as well as measurement, because the world these rocks formed in is so different from the present that direct analogies are often misleading. There were no plate tectonics as we know them, at least not yet. There were no continents in the modern sense. There was no oxygen in the atmosphere. The oceans, if they existed, had a completely different chemistry. Even the day was shorter, the moon was closer, and the tides were higher. When a geologist says that certain chemical signatures in an ancient rock suggest the presence of liquid water, they are making an inference across an almost unimaginable gulf of time and environmental change. They are reading a language written in minerals and isotopes, translating it through models and comparisons, and careful, cautious reasoning. It is one of the most demanding intellectual tasks in all of science, and it is done quietly in laboratories scattered around the world by people who have dedicated their lives to the patient reading of the oldest pages of Earth's autobiography. After the Hadean came the Archean, beginning around 4 billion years ago and lasting until roughly 2.5 billion years ago. This was the age in which the Earth began to leave a more substantial record. Rocks formed in the Archean are still found on every continent. They are old beyond easy comprehension, but they are not the near-vanished ghosts of Hadean crust. They are recognizable, mappable, and in many places, still forming the deep structural foundations of the land. The Archean world was a strange and beautiful place by any standard. The sky was a different color. Without significant oxygen in the atmosphere, there was no ozone layer to scatter sunlight in the way it is scattered today. The sky may have appeared a pale orange or a faint yellow-gray, tinted by the methane and carbon dioxide that dominated the early atmosphere. The sun itself was younger and cooler, burning at perhaps 70 to 80% of its current brightness. And yet the Earth appears to have been warm enough for liquid water to cover its surface. The greenhouse gases in the early atmosphere compensated for the fainter sun. The oceans were warm, probably warmer than any ocean today. They were also chemically different. Iron dissolved freely in the deep water because there was not yet oxygen to oxidize it into insoluble rust. The chemistry of the oceans more closely resembled a dilute mineral broth than the salt water we know, and life was already there. The oldest unambiguous evidence of life in the rock record comes from the Archean. Stromatolites, layered mound-like structures built by communities of microorganisms, have been found in rocks around 3.5 billion years old in the Pilbara region of Western Australia. These are not complex life. They are microbial mats, communities of single-celled organisms, most likely related to modern cyanobacteria, building their layered homes in shallow coastal waters. But they are life. They are metabolizing, growing, reproducing organisms. And they were doing so 3.5 billion years ago, in a world without oxygen, without predators, without any of the ecosystem complexity that would eventually emerge. The Archean stromatolites are among the most quietly extraordinary objects in all of natural history. They look like simple, layered rocks, their surfaces worn and patinaed by age. But if you know what you are looking at, they are the work of living things. The oldest living things whose structures are clearly preserved. Communities of organisms that built homes and left them in stone for 3.5 billion years, waiting for us to find them and understand what they were. The Archean left a specific and fascinating record in what geologists call greenstone belts. These elongated strips of ancient rock are found on every continent, often nestled alongside the ancient granite cores of the cratons. They are called greenstone belts because the volcanic and sedimentary rocks within them have often been altered by low-grade metamorphism in a way that gives them a greenish tint. Greenstone belts are windows into the Archean Earth's surface processes. They contain pillow lavas, rounded masses of basalt formed when lava erupts directly into water and cools rapidly into pillow-shaped blobs. They contain ancient sedimentary layers, compressed and altered, but still telling of ancient seas and rivers. They contain the chemical signatures of hydrothermal vents, of ocean floor volcanism, and of the first cycles of erosion and deposition. Walking through a greenstone belt, if you know what to look for, is walking through the Archean. The rock formations around you were laid down in a world billions of years before the first complex life. The ancient seafloor through which hydrothermal vents pumped hot mineral-rich water. The shorelines of island arcs and early volcanic islands that rose briefly from the Archean Ocean before being subducted back into the mantle. In the Barberton Greenstone Belt of South Africa, one of the best preserved of all Archean terrains, rocks dating back more than 3 billion years have been studied for decades by researchers from around the world. This region in the hills of Mpumalanga province contains some of the most intact record of early Earth processes anywhere on the planet. Ancient pillow lavas lie beside layers of chert, a fine-grained silica-rich rock that preserves some of the clearest evidence of Archean life. Within certain chert layers of the Barberton Belt, fossil microbial structures have been found, tiny, simple organisms preserved in silica as it crystallized from the ancient ocean. These are among the oldest accepted fossils on Earth. Simple, yes, barely recognizable as life if you did not know what you were looking for. But there, 3 billion years ago, in the shallow warm waters around an ancient volcanic island, microbial life was present in such abundance that it left its trace in stone, and that trace still exists, still readable, still connected to the world we live in by an unbroken thread of time. For the first 2 billion years of Earth's history, the atmosphere contained no significant free oxygen. The planet breathed a different kind of air: carbon dioxide, methane, nitrogen, water vapor, but not oxygen. And the record of this ancient oxygen-free world is written in the rocks. One of the most striking pieces of evidence is the presence of banded iron formations, or BIFs. These are layered sequences of iron-rich rock, alternating bands of iron oxide and silica that were deposited in the world's oceans between roughly 3.8 and 2.5 billion years ago. They are extraordinarily beautiful objects. The banding is sharp and precise. The layers alternate between red and dark gray, the colors of different iron minerals. Sliced and polished, they look like abstract paintings. But what they record is not aesthetics. They record chemistry. In the oxygen-free Archean Ocean, dissolved iron was abundant. But then something began to change. Photosynthetic microorganisms, the cyanobacteria, were producing oxygen as a byproduct of their metabolism. This oxygen reacted with the dissolved iron in the ocean, causing it to precipitate out as iron oxide and settle to the seafloor. The bands of iron-rich and iron-poor rock represent pulses of this oxidation, perhaps driven by seasonal or longer-term fluctuations in microbial productivity. For hundreds of millions of years, the oxygen produced by life was consumed by this reaction. The iron in the ocean acted as a buffer, soaking up every molecule of oxygen before it could accumulate in the atmosphere. But eventually, around 2.4 to 2.3 billion years ago, the iron in the ocean ran out. Or more precisely, the rate of oxygen production by life exceeded the capacity of the iron ocean system to absorb it. And for the first time in Earth's history, oxygen began to accumulate in the atmosphere. This event is known as the Great Oxidation Event, and its record in the rocks is dramatic. Before the Great Oxidation Event, certain minerals that are unstable in the presence of oxygen can be found in river sediments and coastal deposits. Pyrite, fool's gold, and uraninite, a mineral containing uranium, both break down quickly when exposed to oxygen. But in rocks older than about 2.4 billion years, they are sometimes preserved in sedimentary deposits. indicating they were transported by rivers and deposited on the seafloor before oxygen could destroy them. After the Great Oxidation Event, those minerals disappear from the sedimentary record. Oxygen had arrived in the atmosphere, and it was transforming the chemistry of the world. At the same time, red beds appear. Bright, red layers of sedimentary rock colored by iron oxide formed when iron-bearing minerals were oxidized in the air or on land before being deposited. Red beds are the fingerprint of an oxygen-rich atmosphere leaving its mark on the land surface. Before the Great Oxidation Event, there are essentially no red beds. After it, they become a permanent feature of the geological record. To hold a piece of banded iron formation is to hold the record of one of the most significant transitions in the history of life and the history of the planet. The moment when a metabolic accident, the oxygen exhaled by microscopic organisms, began to fundamentally transform the chemistry of the world. There is one more chapter in the story of the oldest material on Earth, and it comes not from the Earth itself, but from the sky. Meteorites, particularly a class known as carbonaceous chondrites, are among the most ancient objects in the solar system. Some of them contain material that predates the Earth itself. Tiny grains of minerals formed in the outflows of dying stars, billions of years before the sun ignited. These pre-solar grains, as they are called, are the oldest matter yet identified anywhere. Some of them are 7 billion years old, nearly twice the age of the Earth. When a carbonaceous chondrite falls to Earth and is recovered and analyzed, the presolar grains within it are identified by their distinctive isotopic compositions. They have signatures that could not have formed in our solar system. They are visitors from elsewhere in the galaxy, ancient beyond any terrestrial rock, formed in stellar processes that predate the birth of the sun. The most famous example came from the Murchison meteorite, which fell in Victoria, Australia in 1969. A detailed analysis of grains within it, published in 2020, identified material up to 7.5 billion years old, grains of silicon carbide, diamond, and other minerals that formed inside stars that lived and died long before our solar system existed. These grains were formed inside red giant stars, or in the supernovae of massive stars, or in the outflows of asymptotic giant branch stars, complex stellar objects at the end of their lives, releasing material enriched with the products of nuclear fusion. When those stars shed their outer fat layers or exploded, the material drifted through the interstellar medium for millions of years, before being swept up in the cloud of gas and dust that collapsed to form the sun and planets, and a tiny fraction of it survived the formation of the solar system, survived the accretion of the early Earth, survived the magma ocean and the late heavy bombardment, and 4.5 billion years of geological history, locked inside a meteorite, preserved as individual grains, a few microns across, until a fireball crossed the sky over Victoria one September evening, and a community of farmers and scientists retrieved pieces of it from their fields and sent them to laboratories to be analyzed. Those 7 billion-year-old grains had traveled from a dying star, through billions of years of interstellar space, through the formation of our solar system, through the history of the Earth, and into a laboratory where a scientist examined them under a mass spectrometer and measured the record written in their atomic structure. That is perhaps the deepest time any object in our possession has ever carried. If you wanted to walk across the oldest accessible crust on Earth, where would you go? The answer spans every continent. In Western Australia, the Pilbara Craton is one of the oldest and best preserved pieces of Archean crust on the planet. The landscape here is extraordinary in its austerity. Low, rounded hills of ancient granite and greenstone rise from red plains. The rock surfaces are smooth in places, scoured by 3 billion years of wind and water. Spinifex grass grows in tufts between the boulders. The sky is enormous. Here, you can stand on rock that formed in a world without multicellular life. without complex ecosystems, without oxygen in the air you breathe. The stone beneath your feet was there when the earliest microbial mats were building the first stromatolites in shallow coastal pools nearby. It has not changed fundamentally since. It has eroded and been exposed by that erosion, but its identity as ancient crust has been maintained. In southern Africa, the Kapval Craton in South Africa and Zimbabwe is another of the world's most ancient pieces of continental crust. The Barberton Mountains in South Africa are formed from rocks more than 3 billion years old. They rise steeply from the surrounding plains, their ancient lavas and sediments folded and compressed by billions of geological history, but still legible to those who can read them. In Canada, beyond the Acasta gneiss, the entire Canadian Shield is a vast exposure of Archean and Proterozoic crust stretching across much of central and eastern Canada. It is one of the largest exposed areas of ancient rock anywhere in the world. Lakes and rivers sit in the hollows of its ancient surface. Boreal forest grows over it, but beneath the thin soil and the shallow water, the rock stretches down for tens of kilometers, ancient and unchanged. In Greenland, the Isua Greenstone Belt contains rocks approximately 3.7 to 3.8 billion years old, making it one of the oldest coherent sequences of supercrustal rocks on Earth. Supercrustal simply means rocks that formed at the surface, as opposed to those that crystallized from magma deep in the crust. The Isua sequence is particularly precious because it contains ancient sedimentary layers that preserve clues about the early Earth's environment, including chemical signatures that some researchers interpret as evidence of life, even at this extreme age. And in Antarctica, remote and inaccessible beneath the ice, ancient cratons lie hidden. Only at the ice-free margins of the continent do some of the oldest rocks appear. But isotopic analyses of the rock underlying parts of Antarctica suggest that some of the world's most ancient crust may lie frozen beneath kilometers of ice, beyond the reach of any geologist walking the surface. These places are not destinations in the conventional sense. Few tourists travel to see the Acasta gneiss. The Pilbara Craton is remote and largely without accommodation. The Isua Greenstone Belt requires a helicopter and specific research permit to reach. But for those who do stand on this ancient rock, there is something reported consistently in the accounts of scientists who have worked in these places. A quietness, a sense not of the ordinary geological past, not of the million years of erosion or the 1,000 years of landscape change, but of deep time itself, a depth that pulls at something in the human mind, a recognition that you are touching the first chapter of a very long story. For all that science has learned from the oldest rocks, there is an equal and perhaps greater volume of what remains unknown. The Hadean Eon is essentially dark. We have the zircon crystals from Jack Hills. We have a handful of ancient terrains of debated age. And we have the inferences that scientists draw from the chemistry of younger rocks about what must have existed before them. But the Hadean itself, those first 500 million years of Earth history, is largely a blank, a gap in the record so large that it swallows entire evolutionary experiments, entire cycles of continent formation and destruction, entire chapters of geological history. We do not know exactly when the first continents formed, in the modern sense of stable cratons with thick lithospheric roots. We do not know whether plate tectonics, the great engine that drives the modern Earth, operated in the Archean in the same way it does today. Many geologists believe it did not, that the early Earth operated under a different regime, one characterized by a more vigorous overturn of the crust, smaller and more numerous surface plates, less subduction of the modern kind. We do not know whether life arose once or multiple times. The oldest evidence of life comes from widely scattered locations, and we cannot know whether each represents the same lineage or separate origins. If life can arise once on a planet with the right chemistry, can it arise again? Can it arise simultaneously in different places, under slightly different conditions, producing slightly different initial chemistry? We do not know exactly when the oceans formed, though the zircons suggest liquid water was present by 4.4 billion years ago. We do not know how rapidly the Hadean bombardment declined, or whether there was truly a late spike in impacts, as some models suggest, or a more gradual tapering. We do not know what lived in the Hadean, if anything did. The possibility that life arose before the oldest surviving rocks in the first few 100 million years of Earth history, and was then repeatedly destroyed by large impacts and melting events, only to arise again from surviving populations or from scratch, is entirely plausible and entirely beyond our ability to verify because no record survives. These gaps are not failures. They are the natural limits of a science working at the absolute edge of time. The oldest rocks have told us extraordinary things, but they have also drawn a firm horizon beyond which we cannot see and beyond which we can only imagine. There is something worth dwelling on as you move through this journey into the ancient Earth about what it means for a human mind to encounter deep time. We are creatures of the present tense. Our brains evolved to navigate the immediate environment, to plan a few steps ahead, to remember a few generations back. We are not naturally equipped for geological thinking. When a scientist says 4 billion years, the number passes through most minds like water through sand. It leaves no real trace. We know it is very long ago. We know it is beyond any human reference, but we do not feel it. And yet something changes when you stand on a piece of Archean rock and understand what it is. When a geologist in the field traces the foldeds of ancient gneiss with their finger and says, "This fold happened 2.8 billion years ago, and the one below it 3.1 billion years ago," something shifts, not understanding in the intellectual sense, but something closer to awe, a physical response to the encounter with a depth of time so great that it reframes everything else. The ancient rocks have this quality. They do not demand to be understood in the numerical sense. They ask only to be recognized for what they are. The first solid pages of a record so long that everything we know, every empire, every civilization, every recorded history, is a footnote to a footnote in the final chapter. And there is something deeply peaceful in that recognition, in the acknowledgement that the world was here in extraordinary complexity for billions of years before us, that it will continue for billions of years after, that we are, as so many have said before, a brief flourishing in a very long story. The oldest rocks are not remote from us. They are not separate from our world, preserved in museums behind glass. They are the foundations of the continents we walk on. They are the deep structural memory of the planet. In places, they still poke through the surface. In places, rivers cut through them, and water flows over stone that was old, before the first multicellular organism existed. They are part of the same world, the same restless, changing, enduring world that we inhabit today. One of the most important things to understand about the oldest rocks is how extraordinary their survival is, because the default fate of any rock on Earth is to be destroyed. The rock cycle is the grand geological process by which rock is constantly created, altered, and recycled. Magma erupts from the mantle and solidifies into new igneous rock. Erosion breaks that rock down into sediment, which is transported by rivers to the sea and deposited on the ocean floor. Over millions of years, that sediment is buried, compressed, and transformed into sedimentary rock. When plate tectonic forces carry that rock to a subduction zone, it dives back into the mantle, where it melts and is eventually recycled back into the Earth's interior. Every rock on Earth is in some stage of this cycle. New rock is constantly forming. Old rock is constantly being destroyed. The ocean floor, which makes up the majority of Earth's surface, is almost entirely young by geological standards. The oldest ocean floor is only about 200 million years old. Because oceanic crust is dense and thin, it inevitably sinks back into the hull at subduction zones, destroying its record entirely. The entire ocean floor has been recycled multiple times over the history of the Earth. Continental crust is different. It is less dense than oceanic crust, and so it does not subduct as readily. When two plates carrying continental crust collide, the rock crumples and rises rather than sinking. Mountains form. The record survives, at least for longer. But even continental crust is eventually recycled. Erosion grinds it down. Rivers carry the sediment to the sea. Burial and heat and pressure transform it. And sometimes, where the crust thins or rifts, even ancient continental rock can be pulled back into the mantle. The fact that any rock from the Hadean survives at all is a function of specific geological luck. The cratons, those ancient stable cores of the continents, escaped the most dramatic recycling because they had thick, cold, buoyant roots that resisted subduction. They were too light to sink, too cold to melt, and too stable to be disrupted by the tectonic movements around them. But most of the early Earth's crust did not survive. The record of the first 500 million years is largely gone, melted and recycled, lost to the planet's internal heat engine, which runs on the same energy it has always run on. The heat left over from the planet's formation, and the heat generated by the ongoing decay of long-lived radioactive isotopes in the mantle. Every piece of Hadean or early Archean rock that exists today survived against enormous odds. It was protected by luck or by the peculiar stability of the craton beneath it from the general fate of the crust. It persisted while everything around it was consumed, and because it persisted, we can hold it in our hands. The oldest rocks on Earth are not only a window into our own past, they are also a guide to the search for life on other worlds. When scientists designing missions to Mars, or thinking about the icy moons of Jupiter and Saturn, consider where life might have existed and where its traces might be preserved, they look to Earth's oldest rocks for guidance. If microbial life left its chemical signatures in 3.5 billion-year-old cherts in the Pilbara, what kinds of signatures might life leave in the ancient rocks of Mars? If life began in hydrothermal vent systems on the early Earth, the same systems that are preserved in Archean greenstone belts, might similar systems on early Mars, or on the ocean floors of Enceladus or Europa, have harbored similar life? The study of Earth's oldest rocks is, in a sense, the training ground for astrobiology. Mars is of particular interest because it is known to have had a warmer, wetter period in its early history, roughly 4 billion years ago. This period overlaps with the early Archean on Earth, the time when life was already established in the oceans, and leaving its traces in the rock record. If life arose on Earth by 4 billion years ago, could it have arisen on Mars at the same time? The answer is unknown, but the tools for looking for it, the recognition of biosignatures in ancient rock, the understanding of what microbial life looks like when preserved in chert or carbonates or sulfide minerals, come directly from the study of Earth's oldest rocks. Missions to Mars have already identified ancient sedimentary rocks preserved in the crater floors, minerals that formed in liquid water, conditions that, if they existed on Earth 4 billion years ago, might have supported microbial life. Future sample return missions will bring pieces of Martian rock back to Earth, where they will be analyzed in laboratories using the same techniques developed to study the oldest terrestrial rocks. In this way, the Jack Hills zircons and the Acasta gneiss and the Barberton cherts are not just records of Earth's history. They are the Rosetta Stone for a broader search, a reference library for the chemistry of early planetary life. The oldest rocks on Earth may ultimately help us answer one of the most profound questions in the history of science. Are we alone? There is a kind of thought experiment that is worth sitting with as you rest. Imagine the sound of the early Archean Earth. There is no human voice, of course. No bird call, no insect hum, no rustle of leaves in a forest. The forests do not exist yet. The insects do not exist yet. The birds are hundreds of millions of years away. Even the fishes are not yet there. What you would hear is the ocean. The Archean Ocean stretched across much of the planet. It was shallower in some places than the oceans we know for, because the continents had not yet grown to their present extent, and the seafloor in many regions lay close to the surface. Its waves broke on bare rock shores, on volcanic coastlines still steaming from recent eruptions, on the rounded humps of ancient granite islands rising from the warm water. Those waves would not have sounded entirely different from the waves you know. The mechanics of water and wind and shore are the same, but the silence behind them would have been profound. No biological activity producing sound in the air, no call, no song, no scratch of claw on stone. Only the ocean and the wind, and the occasional rumble of volcanic activity in the distance. The wind, too, would have been familiar in its mechanics, though the atmosphere it moved through was alien. Thick carbon dioxide, methane, nitrogen, no oxygen. A wind that would have been lethal to breathe, carrying smells of a world whose chemistry was entirely different from ours. And underneath the surface of that ocean, in the warm shallows near hydrothermal vents, in the microbial mats beginning to form on the seafloor, there was the quiet chemistry of life. No sound that a human ear could detect. Just molecules combining and dividing, energy being captured and used, waste being released. The deep, silent engine of the first living world. That engine is still running. 3.5 billion years later, it is still running. In every cell of every living thing on Earth, the same fundamental chemistry that operated in those Archean mats is still at work. Modified, elaborated, diversified beyond all recognition, but still fundamentally the same process. The oldest rocks on Earth are not only a record of the planet's past, they are a record of the beginning of that engine, the first chapter in the story of life's unbroken run from the early Archean to the present moment. And that connection, that unbroken line from the ancient stone to the living world, is perhaps the most extraordinary thing of all. The mystery of Gondwana is written in the oldest rocks. Long before Pangaea, there was Gondwana, the great southern supercontinent that united what would become South America, Africa, Antarctica, Australia, and India. And before Gondwana, there was Rodinia. And before Rodinia, there were unnamed assemblages of crust that drifted and collided and drifted again over the first 2 billion years of Earth history. Each of these ancient supercontinents, assembled from the same ancient building blocks, the old cratons, whose roots reach back into the Archean and sometimes the Hadean, and each time the continents assembled, they left their mark on the ancient rock. Collision zones, mountain roots, metamorphic belts where old rock was reheated and recrystallized by the pressure of converging plates. When you look at the distribution of the oldest rocks on Earth today, you find them scattered across the cratons of every continent. But the patterns in which they are scattered, their ages, their compositions, and their structural orientations, tell the story of all those ancient assemblies. Like pieces of a puzzle scattered on a table, the oldest rocks still carry the information needed to reconstruct the lost supercontinents that no living eye ever saw. This is one of the most remarkable uses of the geological record. By measuring the magnetic orientation of ancient rocks, scientists can determine where in the Earth's magnetic field they were when they formed. Because the magnetic field aligns with the planet's axis, this gives a paleolatitude, a sense of where on Earth that piece of crust was located at a given time in the past. By combining magnetic data with radiometric ages and geochemical fingerprints, scientists have reconstructed the positions of the ancient continents at various points in deep time. The results are humbling. At various points in the Proterozoic, 1 billion years ago and more, the Earth's landmasses were arranged in configurations so different from the present that they would be entirely unrecognizable on any modern map. And the oldest rocks, the Archean cratons, were there through all of it, drifting from latitude to latitude, colliding with and separating from other cratons, accumulating new rock at their margins, while their ancient cores persisted unchanged. They have been to the tropics and to the poles. They have been the hearts of great mountain ranges and the flat, eroded floors of ancient plains. They have seen more of this planet's geography than any living thing ever could. There is a practice in some geological communities of gifting a small piece of ancient rock, a chip of gneiss, or a fragment of greenstone, to a colleague or student as a gesture of connection to deep time. The gift is modest in material value, but rich in meaning. It says, "Here is a piece of the world's beginning. Handle it with care." Whether or not you have ever held a piece of Archean rock, the oldest stone is always somewhere beneath your feet. Drive through the Canadian Shield. Walk in the Pilbara. Climb in the Barberton Mountains. Or simply understand that the continent you stand on, wherever you are, is underlain at depth by ancient crust. That somewhere beneath the layers of younger rock and soil and sediment that make up the surface world, the old foundations remain. The world you live in is built on rock that was old before life was complex. The mountains you see, even the young ones formed in the last few tens of millions of years, are ultimately erosional products of that ancient material. Their sediments are ground down Archean and Proterozoic rock, redeposited and recompacted. The iron in your blood was forged in supernovae before the solar system formed, and was cycled through the ancient ocean and the Archean seabed before finding its way into the chemistry of life. You are, in the most literal molecular sense, made of ancient material. The atoms that compose you have long histories. Some of them have been through multiple stars. Some of them were part of the Hadean Earth. Some of them passed through the first living cells in the early Archean ocean. The oldest rocks on Earth are not a distant curiosity. They are part of the same story you are part of, a story that began 4.5 billion years ago in a magma ocean under a young sun and is still being written today. Night is settling in now. The questions we have walked through tonight, ancient though they are never entirely finished. The scientists will return to their laboratories tomorrow. New zircons will be analyzed. New outcrops in remote places will be described and dated. New interpretations of old data will be proposed and debated. But for now, let the oldest rocks rest in the quiet they have always kept. They do not ask to be understood. They do not need to be. They are simply there, as they have always been, patient and unchanged at depth, while the world above them restlessly rearranges itself. Mountains rise and fall above them. Oceans come and go. Life experiments and diversifies and occasionally suffers catastrophe and recovers and diversifies again. Ice ages come and melt away. Civilizations rise in the blink of a geological eye and collapse, and the old rock endures. In the deep Canadian Shield, under the northern lights and the boreal winter, it sits in the darkness beneath the snow, 4 billion years old, and utterly unmoved by the passage of the seasons. In the red Australian outback, under the enormous southern sky, the Pilbara craton lies baking in the sun as it has for 3 billion years, its surface worn smooth by an eternity of wind. In the mountains of South Africa, among the birds and the trees and the afternoon light on the ancient snow, the Barberton rocks hold the oldest unambiguous traces of life, quiet in their record of a world that existed before anything complex had yet learned how to exist. These places are not monuments. They were not made to be seen. They were simply made, in the first chapter of the world's history, by the same processes that have always operated: heat, pressure, ancestry, time. They are the oldest pages of the longest book, and the book is still being written. Let that thought carry you now into the deeper quiet of sleep. Let the ancient stone sit at the edges of your awareness, patient and permanent as it has always been. Let the weight of deep time settle over you like the gentlest of shelters. You are a brief, luminous moment in a very long story, and that story, from its first broken fragment of Hadean crust to the world you know now, has been In all its strangeness and complexity and endurance, extraordinary, the oldest rocks are still there. They will be there tomorrow, and long, long after the last light.